Good morning, good afternoon, and welcome to a conversation on 3.5 and CBRS in the US and more generally on spectrum sharing worldwide. This is becoming a very hot topic as we address the need for additional spectrum as we increasingly use more and more data and we move to 5G. And today in this conversation, I'm talking to Nebu John Mathai, who is the Director of Strategic Initiatives and Advanced Engineering at Cognitive Systems. And Nebu, thanks for being with us today.
Thank you.
Okay, to get started, can you tell us a little bit about Cognitive Systems? What is it you guys do?
Sure. So with respect to CBRS and related government and industrial markets, I guess you could look at Cognitive Systems Corp as a provider of a full stack solution for radio frequency sensor networks for a whole variety of RF situational awareness problems, ranging from spectrum sensing, spectrum monitoring, spectrum management, and of course the holy grail of dynamic spectrum access. So we provide a full stack solution. By full stack, I mean we start at the silicon level because if you want to do RF sensor networks, you have to make sure you have a high performance solution that also has low size, weight, and power footprints, because that's what makes a sensor network mass deployable, right? That's what makes it practical. So for us, we had to address it from the level of building a very aggressive piece of silicon, our R10 cognitive radio integrated circuit. Then the sensor node on top of that, a secure sensor node, because usually when you sense spectrum, that's of strategic interest. And the relay back to the backhaul has to be secured. And finally, the cloud backend for this whole sensor network to ensure that device can be tasked in a secure way and that data can be taken, fused, analyzed, in a very expedient manner. So we're a full stack RF situational awareness, RF spectrum sensor network company.
Okay, now sensing the spectrum, you want to know what's going on, but this is particularly important in 3.5, well, in the US and right now. Can you tell us a little bit about why do we need to know what's going on in terms of RF usage?
Generally for spectrum or
for 3.5. I mean, well,
okay, yeah. Well, that's a great question because that difference is what makes what poses the greatest requirement on the type of sensor network you put. Sensing spectrum is a relatively straightforward problem. There's a variety of solutions for it. With CBRS, though, it's not about sensing spectrum. It's about finding the incumbent, because the objective in CBRS is to protect the incumbent user, because the incumbent user is the federal government, and it's a very strategic user of it. And so the bar is set very high. So not only must you, it's not just a pure sensing spectrum and let's get the data. It's identify where the incumbent is as expediently as possible, make that a very positive identification and relay it back to the spectrum access system so that, actions can be taken to that's how the whole scheme works. Mm-hmm. So yeah, in this case, the spectrum sensor or the RF sensor network has to be of a sufficient level of performance to be able to not just merely sense spectrum, but find the incumbent user in there, possibly buried within LTE.
Mm-hmm. Right, and the legacy users can be using the spectrum anytime, any place. So I guess that they're not going to completely randomly show up, but it's possible. So you need to be able to everywhere be able to see whether there is something coming up in real time, pretty much, right?
Yes, that is exactly the operating assumption for us. I mean, it is the operating assumption for ESC, the environment sensing capability. The incumbent user is giving you no feedback, is giving you no information a priori as to where it is. and how it's moving. So you have to be able to detect parts of him, right? Parts of the signal, to detect the signal, probably not in the most cleanest of circumstances. So it's actually it's a very interesting problem. But for us, we actually find the characteristics of ESC sensing sort of really allow us to demonstrate our high performance solution very well, because there's lots of computational aspects to it, like to determine, to find this incumbent and to positively identify it. And it very well exploits the high level of computation that which we have integrated on our integrated circuit.
So is it the issue not just to find spectrum, but to identify legacy user as such? So it's legacy versus a general access user or something.
Right. Yeah. And I think that the question is, I mean, the problem is you're going to have these general access users who have been allowed into the band, and you're going to have the legacy user. And you must find when the legacy user is active to ensure that the spectrum access system can move the new users away from that band so as to protect the incumbent.
Mm-hmm. Right. So yeah, so it's now, is this a new issue, or have you seen that similar issue in terms of spectrum sensing before in our bands?
I think CBRS represents a very bold new step in the fact in the sense that it is a dynamic spectrum access system in all its glory, right? It is, there's a spectrum, so to speak, of spectrum allocation techniques. There's fixed allocation. There's database-based allocation, where you have an open loop database. So the users can share spectrum. They appeal to a database to find out where they should be. But there's no closed loop feedback to determine whether collisions have occurred and things like that. There's a half step above it, which is what NOAA does. They have a scheme, I think they call it cooperative spectrum sharing, between the SATCOM ground station links and LTE users. And that one, it's still different from CBRS, because in that the sensor network is in place to in a forensics capacity, right? To after the fact inform when collisions have occurred and to sort of manage the problem. I think the beauty or the interesting aspect of CBRS is that it is a closed loop spectrum access system, and to my eye, I think it's probably the boldest, if not the first one, which seeks to integrate the user equipment, the SAS, the spectrum access system database, with a closed loop dynamic element with the environment sensing and control.
Yeah. So that raises the issue of how do you interact with the SAS? Because obviously you need to work closely to make sure that all the dots are connected. Yeah. You sense the spectrum and you take appropriate action.
Well, and that's, I think, a lot of the discussions in WinForum pertain to that, right? The SAS CBSD interoperability and the SAS ESC interoperability. And how do you get these messages from the fusion engine of the ESC, the cloud backend for the ESC, to the SAS. So it is, I think it's a topic of active discussion. For us, we address the problem from providing a spectrum sensor, which can be mounted in outdoor infrastructure, which has been validated across temperature and power and in various sweeps, with a cloud backend for it, a reference cloud backend for it, which can be used to task manage and extract the traffic, or extract the measured parameters from the spectrum sensor.
So your solution is designed to work with a SAS or within a SAS, is that right?
No, it's fully on the ESC side. It's for the there's a notion of the ESC operator. It's for an ESC operator. To the ESC operator, then there's an ESC protocol, the interoperability protocols between ESC and SAS.
Okay.
So that end would be managed by them, but I think one of the most technologically challenging aspects is how do you have a outdoor capable, CBRS sensor, which can aggressively find the incumbent and report presence of that incumbent to the ESC fusion point for it to relay back to the SAS.
Yeah.
We don't look at the ESC to SAS links yet. We're actively listening to how that is playing out in wind form. And certainly, for us, the bridging between two clouds is not so much a major problem. Once that converges, once that discussion converges, we'll be well posed to offer that end. At the same token, there's the nature of ESC operators are heterogeneous. Some solutions, some are focusing on the back end solutions. Some are looking at the front end solutions. We feel that it's unlikely that with off-the-shelf components, an aggressive spectrum sensor for ESC can be realized. I'm sure it's easy to prototype something that may work in the lab, but I think what we offer is something that's productized. We offer this, an IP67 encased spectrum sensor. And that's, it requires no more power than what you can give it over power over Ethernet. Right. And I think it's a different kind of spectrum sensor by an order of magnitude, right? Yeah. It's one that sort of optimizes and gets you to a sweet spot of extremely high performance with low size weight power, which usually are diametrically opposed trends, right?
Yeah. So where would you install them? Because you can say, well, you want to have a nationwide, so that you can sense spectrum utilization everywhere. But there are a lot of places in the U.S. where obviously there is no 3.5, either legacy or non-legacy. So where would you put the hardware really?
Well, I think the prime benefit of because I think the first phase of CBRS is where they allow the CBSD devices to operate further inland, and thereby, by design, not interfere with the incumbent user. But I think the stat was 45% or some large fraction of the population of the U.S. is actually closer to the coasts, right? And when that happens, you do need to have the EC activated, right? Because the chance for contaminating and interfering with the legacy user starts to pop up. So I believe the main place where these sensors will be put will be relatively close to the coast, within 100 kilometers. Right.
And how distant would they be from one to the other to make sure that you cover the entire area?
That's a great question. And I think that's actually a very good question. It actually touches on a couple of things, because one, there are various papers and studies in which people have claimed numbers that range anywhere from hundreds or even less to the higher thousands. But if you look at it, and the sensor network problem is not something that can be actually solved a priori. I'm sure you can use forecasting engines and simulation, but fundamentally for any sensor network, not even RF, the whole idea of sensor networks is you get better situational awareness of your field of data with the more sensors you put in. And it would be very non-ideal if we go into CBRS ESC, if we go into CBRS thinking that, okay, a certain number of ESC sensors are suitable, only to find, and then, if the number is low, then you could start to look at very expensive, large systems, right? I still feel that expensive and large systems are unlikely to have the agility to detect the incumbent randomly, but let's assume that they can, right? So you start to admit this idea of, okay, let's just use a really big piece of test equipment and network it to some back end. I mean, at a very elementary level. The problem with that is though, when CBRS starts in all its glory, right, and it's all in its fully dynamic glory, and you find that, there are some aspects of our forecast which are not correct, then what do? The scalability of a sensor which has poor size, weight, and power characteristics is limited, right? So we feel that for CBRS and beyond, it is important to look at a very advanced class of sensor, which will have high performance and offer the low size, weight, and power, which will enable you to distribute it in, in a mass form. As well, I mean, that doesn't even touch on the whole idea of there will be a need for a forensics network, possibly, right? There is some discussion about not only realizing the ESC network, but at some point have more sensors elsewhere to ensure that the forensic task is addressed, right? Because whenever you, sorry. Oh, I was just going to say, whenever you have, regardless of the spectrum allocation mechanism, when you talk about, even for fixed allocations or data-based allocations or dynamic spectrum access allocation, there is always going to be a forensics issue, right? There's always going to be the idea of people interfering inappropriately and so forth. And so, yeah, so the answer is this: I don't have an answer for how many sensors you will need. I can't forecast that. I've heard the numbers, and the numbers are all, very reasonable. But my perspective, and I think, the perspective of our company and with appeal to our advanced technology here, is that regardless of what that number is, the spectrum sensor or the sensor that is, that can be used for the ESC function should be able to have favorable mass deployment characteristics.
Right. And then I guess that you need to know, because I guess that depending on the specifics of the location, the topology, you might need higher or lower frequency depending on, of course, and things like that. So
yes, yeah.
Yeah. Now you mentioned forensic functions here. I guess this is something that the legacy users are going to require, or is it mostly, to make sure that they feel comfortable, or they know what's going on? Is that?
Well, no, I don't want to say that because it makes it seem as if forensics is required for CBRS. In fact, if you look at it, there was in 2016 there was the ISART conference in Denver. The theme of that was spectrum forensics, and it isn't because of dynamic spectrum access. It's because for every the spectrum, RF spectrum has economic costs. It's precious, and it has strategic and tactical is of strategic and tactical use to the government. So there is a very important forensics problem with spectrum, even without dynamic allocation, right? Yes. And the interesting thing is this, and the alignment is very fortunate here, because at the time, people have been talking about, well, how do you do spectrum forensics? Well, how should we do spectrum forensics in the future? And the current way of spectrum forensics is obvious, right? If it's outdoor spectrum you're dealing with, you do drive tests. If it's indoor spectrum, you do walk tests. And then you have this massive data. And then hopefully, several hours later, you go through that data and try to find the transient event that caused the problem, right? Which is a very difficult prospect. So to address that problem, people have been talking about, okay, well, why don't we ride some spectrum sensing functions on the LTE infrastructure? That's an interesting idea because it's already been deployed, it's in place. Certainly from that perspective, everything is fortunate. The problem is this: the computational intensity to do spectrum analysis across a wide band is actually high. And and I don't say this as a base station expert. I say this purely because the comment that the person who proposed it indicated was that due to the rate of compute that they had to run, they would have to lower the duty cycle of how often it does the spectrum sensing function, which is a problem because when you lower the duty cycle, you reduce your probability of catching transients, right? Interference problems are all transients. They're not steady state. If they were steady state, they're easy problems to find. The hard problems are the transients. So now coming back to CBRS and how this all aligns. With CBRS, with dynamic spectrum access, you have a requirement for the infrastructure to be in place in which there is a spectrum or in which there is a sensor network. If you choose your spectrum sensors properly so that they're not single function spectrum sensors, but spectrum sensors that can be retasked and that have the compute power to run multiple operations simultaneously, then you're shooting basically two birds. You're hitting two birds with one stone, right? You're putting in place a sensor network to protect the incumbent. That's the DSA task. And you're simultaneously having the infrastructure for forensics in place. If you choose the spectrum sensor,
you get it for free, right?
If and only if you choose the spectrum sensor properly, right? If you take some off-the-shelf components and you try to rig an ESC sensor, you probably can. But the likelihood of that being applicable for multiple tasks is probably going to be low, because the technology that's used for current spectrum sensing does not have ideal size weight power. So you're playing a game between size weight power and compute performance and cost, right? So that's why I just added the proviso. If you choose the type of spectrum sensor and put it in place in which it does have a high performance element, it does have spare compute performance, then yes, you will have, you'll achieve two goals with one deployment.
Now, some of the 3.5 CBRS deployments are going to be indoors. Do we need to do spectrum sensing indoors too?
Well, so I'll leave that question to the experts on whether CBRS will need it. Merely to put this point, fundamentally for us, from our perspective, even if, whether or not it needs it would be immaterial to us. Our spectrum sensors are deployable indoors or outdoors. There's actually a broader problem with indoor wireless, even without appeal to CBRS. Outdoor wireless is hard to do, right? It's an art, and that's why the people who do it hopefully make a lot of money doing it. Indoor wireless will be harder because the problems and the challenges in indoor wireless are quite difficult. You have environments which are hard to characterize, which are dynamic. You have populations of people who move around, which alter characteristics. And of course, when you're indoors, especially with modern building materials, the likelihood of you having access to outdoor wireless is sometimes limited, especially underground and in those types of environments. So it's important to have a very solid indoor wireless infrastructure. What I think is reasonable to think is that in the future, indoor sensor networks will be a thing, because we have, indoor wireless has all of these nice deployment mechanisms, DSA, sorry, not that, the antenna systems that are, these special types of antennas and mechanisms like that. But do they have live feedback to allow the antennas to tune themselves? I don't know. I don't think so. From what I've heard when I go to these indoor wireless events and hear the discussions, I don't think the infrastructure is in place to do aggressive spectrum sensing indoors. So my answer to your problem was I'm not going to give an answer with respect to CBRS, because there are far more, the people who are doing these discussions are, there are discussions in place to understand those characteristics. But I think it's fair to say for us, from my perspective, that the sensor network that we have, or the sensor technology that we have, is as deployable indoors as it is outdoors.
Yeah, well, that's interesting. I guess it just brings a sort of a broader issue here. Now let's move in a bigger dimension, in a different way, in a different perspective. CBRS in the U.S. What is that going to do for spectrum sharing worldwide and in the future? What do you think that the role is going to be?
Well, I think if you look at it, CBRS has gotten a lot of attention in a variety of places outside the U.S. Right? In Mobile World Congress, significant references to CBRS, and also when I've talked to European, to interested parties in Europe, there is a sense you get that folks are looking at CBRS in the U.S. as an exemplar to show that dynamic spectrum access not only is it possible, and of course it's possible, but that it's practical, that it's as high performance, its benefits are as advertised, right? So I think there's a very important aspect to CBRS in terms of demonstrating that DSA is a way to go forward, because there are a variety of interested parties, naturally in any economic system, with varying opinions on CBRS and DSA, right? But what is finally incontrovertible is physical reality, and that is that spectrum is in finite supply. So worldwide, spectrum and the problem of the spectrum crunch has to be addressed. DSA is a very nice way of addressing that. So what would be very fortunate is for a successful exemplar of DSA to to be, the visibility of the success of CBRS helps to show that DSA is a viable paradigm, and I think that's what the broader implications of CBRS are.
Yeah, and hopefully that's gonna happen, because, as I say, there is a huge need here. Well, Nebu, thanks so much for sharing your thoughts with us today.
Well, thank you very much.
And this was part of a conversation for a report on 3.5 CBRS and spectrum sharing by Sensafili in collaboration with RCR Wireless. And thank you all for listening in.